Hello, this is part 2 of my videos on expectation algebra, and in this case we're going to start looking at two variables. And whilst I want to get to this general case here, I'm going to next start off with a simpler version where our new variable x is a combination, sorry, z is a combination of x and y. So the one in the textbook is Z will be the length of a cricket bat, and X is the length of the handle, and Y is the length of the blade. Yeah. So what we want to do is to find the expected length and variation in the length of the combined the full total cricket bat. Okay. So let's have a look at what we can do using our new formats. So our expected overall length is the expected x plus the expected y. Now, if we just look at that as basic probability, we need to have our variable, which is x plus y, there, and the probability of that pair of x's and y's, yeah, because we could have a whole range of x's. The length of the cricket bat might be between, the handle might be between 20 and 30 centimeters, and the length of the blade itself might be between 40 and 60. So we've got a whole number of combinations here. Yeah, that's equivalent to rolling a dice. We'll come back with an example of rolling a 1 on the first dice and a 6 on the second dice. Yeah, so these have been given because they're two different variables. We've got I is for all the variance of the x, and j is for all the variance of the y. And here's our probability of the two, and that's going to be the intersection, isn't it? If we were drawing this as a Venn diagram, that would be our intersection of those two occurring, the xi and the yj occurring. Yeah. Now, the biggest thing for this expectation approach is that these two variables have got to be assumed to be independent, because if they're independent, then that probability there can be rewritten, can't it? It's the probability or that x is the xi, and the times the probability that the y is the yj. Yeah. So effectively we've split that into a multiple of two separate independent probabilities. So if we then go on from there, then we therefore can rewrite the probability we had just now with our two probabilities split out, and there's our variable, and effectively we're finding the weighted average of this variable here when it's weighted by both probabilities. Now, as we saw before in the simpler part 1, we've got an addition here, so we can split that into two terms, can't we? One term is what happens with our xi. Sorry, let's go in the right direction, shall we? There's our xi. And the other term is what happens with our yj. So I didn't put a j there, did I? There we go. And they're going to be added together. So on the left hand term here, we've got the sum over all i's and j's of xi times the probability of xi and py probability of yj. Yeah. Now that's actually a big array of numbers because we've got both of these varying, haven't we? We've got the i's varying, the xi's varying, and the yj's varying. So effectively we've got like a little table here, and what we can see is we can split this because these two are just functions of xi, so we could put that together into one sum, and this here is just a function of the yj, so that can be in the second, that can be a sum. And because effectively we've got a table here, we're going to multiply those together as we've got a little set of variables, haven't we? We'd have a load of numbers going this way and a load of numbers going that way, so in effect and we're taking what's going on in this direction and multiplying it by what's going on in this direction. Okay, and if we have a look at that, well, we know that this first part of the term here is xi times the probability of xi, so that's the expected x, and the second one is the sum of all our probabilities of yj, and of course all they must add up to 1. So the first term here is expected x. And let's have a look at the second term. This is our y, there shouldn't be a b there, excuse me. This is our yj times the probability of x and the probability I and probability of yj. And of course here we can split that in a different way, in that j and this probability are only functions of yj, and this one, the probability of x, is only a function of probability of x, and therefore we can again split this as if we're doing a little multiplication again, and we can separate that out. So we've got our probability of x's, and then we've got our j times the probability of j, so y, and they're multiplied together because it's in this table one by the other. And therefore the first part of that is again the sum of all the probabilities of x is going to be 1, and the second here, the j, so yj times the probability of yj is the expected value of y. So what we've just proved here is the expected value of x plus y is the expected value of x plus the expected value of y. Yeah, and that all works because they're independent. Now let's have a look at what we've got to do with the variances. So following the same sort of strategy, we need, first part we need is our e of z squared to go into our variance. So here we've got our same sum over all the ij's. We've got our variable, which is the xi plus yj, all squared, and then we're weighting it by the probability of xi and the probability of yj. And again, we expand the first bracket as we did with single variable. We expand the bracket, and now we've got effectively 3 terms here added together, so we then split that up. So our first term here is our xi squared times the probability of xi times the probability of y of j si yj. And if we have a quick look at that, we can again split that into 2 sums. One of the i's, the xi and the probability of xi, there we go, xi squared and the probability of xi there, which of course is, we know that to be the expectation of x squared. And in the second part, we've got our probability of yj all summed up, and we know that all of those summed together equal 1. So there's our first term, expected x squared times 1, that's expected x squared, isn't it? Now I'm just going to move it up slightly so that we can see that. Let's have it like that, shall we? There's our first term, expectation of x squared. Now let's have a look at our middle term here. Well, our middle term here, what came from our 2xi yj, here's our, and when we split that out, we can take the 2 out the front because that's a constant, and that that ij should be under there, really, shouldn't it? There's our ij going under there. And then we've got our probability of xi and our probability of yj. Now, we can again split this up and take all the things that are functions of xi. Yeah, so xi times probability of xi, put that in one sum, and multiply it by the probability of y and the yj and the probability of yj, because again we're doing a little table multiplication. Therefore we end up with 2 lots of this first part here is the expected value of x, multiply, and the second part is the expected value of y. So our middle term is 2 times the expected value of x times the expected value of y. And what happens with the y, the final term, our yj squared, well, that comes over here for our final term, and again we can split this up. So we've got our element that's only dependent on xi, so that's that there, and then we're going to multiply it by our yj squared times the probability of yj, and we know that final bit is the expected value of y squared, and the first part is again the sum of all the probabilities of x, which is going to be 1. So our final term is expectation of y squared. Okay, so that's our, we've now found ez squared, And of course, if we want to find our variance, we know our variance is that term that we've just calculated and our expected value of z all squared. So here's our first part that we just found for e z squared, and we already know that the expected value of z is just the expected value of x plus the expected value of y, and that's squared. So if we expand that bracket, we get this expression here. Now we just need to rearrange the terms and see what happens. If we take the first term from the ez squared, there's our e of x squared. And if we take our first term from our expected z all squared, we get an e to the x all squared. And that lot we know together, we know gives us the variance of x. Let's have a look at the final term, because I think that might help us. Let's have a look at the final term here. Here we've got our ey squared in this bracket, and there we are. And we've got ey all squared from the second bracket. So if we put those together, and we find that that's those two terms together, we know that that's the variance of y, don't we? That just leaves the terms in the middle. Well, here we've got the expected value, 2 times the expected value of x times the expected value of y, but then we've got a subtraction here from the second bracket of exactly the same. So those two terms are going to cancel out. Okay, so what have we done? We've fairly quickly proved that the expected value of the variance of xy, expected variance of x plus y, is going to be equal to the variance of x plus the variance of y. So that's quite useful to know, as long as these two, x and y, are independent. And that's the key point. So that's going to be my part 2 video. We've found that and gone through the expectation and proved that. So that's the second part.